different ways of measuring delta H's will not always give you the exact same value, but they'll be close. They'll be close. Since these are what they are, should we just take the average if we want to do something with these? I mean, there's one of these you like better than the other one? Trust one more?
I kind of feel number one more.
You like number one more?
Yeah.
Does anybody like number two more?
I like number two because
We're going to take the average then. The average is 28.6 kilojoules is the delta H for this reaction. Now, with that as the delta H of the reaction, try to answer number 3 now. Now we have to add a bit of stoichiometry. Because I don't have a whole mole of baking soda in number 3, I only have 4.2 grams of it. So what would be the change in energy if 4.2 grams of baking soda reacts? Let everybody do it.
okay. But I got it first though.
That's important.
I got it before we came.
Just to speed things up, the molar mass of this is 84.
That's
Yeah, just got the
How are you? Already do. I just put two ones in.
That's fine.
Quiz, yes. Test, free response, yes. Multiple choice, no. Okay. Do you have an answer for number 3? 2 sig figs? Positive, right? How much do you want for? I think. With, is it 1.5? Oh, okay, okay. So yeah, you make it 1.5. Can we actually do this reaction and measure how much energy what the delta H would be?
Yes.
How do we measure heat? Temperature thermometer.
You measure the transfer.
Yes, we measure the transfer of heat with calorimetry. Notice that I have 2 cups, one nested inside of the other. That's the way we'll always do calorimetry reactions or experiments. Because styrofoam is a very good insulator, but it is kind of thin, so I'm using 2 just to double the amount of insulation. So I have measured out 100 ml of hydrochloric acid, so that's going to provide the hydrogen ions. I also have measured out 4.2 grams of baking soda, which is that. So I've already got that on a piece of paper. I'm going to add the 4.2 grams to my calorimeter. It's a spectator, yeah, it does nothing. And I have a thermometer. Would you tell us what the initial temperature of the hydrochloric acid is? Well, how long you want to wait? Okay. Just see if it's changing. The room is room temperature, the water, the acid is room temperature, so it shouldn't change much when you agree?
Is the air in the HCl kind of...
Yeah, it's been sitting out since last night. 23.5, right? What is it? 24.0. Okay. That's fine. So we have an initial temperature of 24.0 degrees Celsius that we're about to start our calorimetry experiment with. This reaction, is it endothermic or exothermic? Endothermic. So when it's happening in water, what is happening to the water? The reaction, the process in the water is endothermic. So it has to take energy in. From what? From the water. So when we have a thermometer in the water, what will we see happening? We expect the thermometer to show a decrease in the temperature. Well, we're going to find that out. We have also, just to say what our variables are, we have a single 100 ml, which is 100 grams of water. We have, that's the mass. The C for water, we know, is 4.18 joules per gram degree Celsius. Now, you know that this isn't pure water. This is hydrochloric acid that I have. But it's close enough to 100 ml and 100 grams of water. Okay, so now we're going to run the reaction. We're going to find what the new temperature is. I already have the baking soda in here. So as quickly as I can, and I'm going to have you guys do this, you take the lid. You got the thermometer. And as quickly as we can, we're going to add the acid. Now you know that acid and baking soda is going to fizz up. So I'm going to not add too fast so that it splatters out. I don't want it to splatter out. But fast enough so that we can get the heat as much as possible trapped in there and we don't have any effect from the surroundings. So, ready for this? I'm going to try to go pretty quickly. Now you can hear it fizzing. Ah, okay. Now go ahead. It's not going to explode, KF. You got it, Jennifer. I'm going to let it go. All right, give it a stir with the thermometer. Keep it moving, and watch that temperature. Yeah, they're just going to watch it for the lowest temperature that it achieves. Okay. Is it going down? Yeah. So they don't insulate perfectly. I mean, if it was a perfect insulator, you would not feel anything on the outside. Like a thermos, thermos, you don't know what's going on the inside. It's fine. You're okay with there? All right, what's your temperature? To the 10th place. What? 21.2? Okay, so we have all of the information that we need to find out how much heat the water gave to this reaction. Do we not? What? What did you say, Jan? Oh, yeah, I just didn't hear what you said. That's right. So the Q of the water equals MC delta T. Can you go ahead and calculate that? That was 100 times 4.18 times, what was our delta T? 2.8? 2.8? 117, so we're going to call it 1200 to keep it to two sig figs. That was, and by the way, the delta T was negative, so that number is negative. Q of the water is negative 1200 what? 1200 unit? You remember what the unit is on the C? It's joules. Not kilojoules, it's just joules. Convert that to kilojoules. I was getting all excited when you were saying that it was going down to 20 degrees, because yeah, you do need a little bit more than 3-degree change to get this exact. But we calculated that 4.2 grams of baking soda should take in 1.4 kilojoules. How much did it really take in? 1.2. Do you believe in calorimetry?
Yeah.
Pretty close, isn't it? I mean, we've got a couple of hacks here that are doing our experiment for us.
Yeah.
Just kidding. You guys did a wonderful job. Wonderful. Is it still down up above? We didn't get to our lowest temperature. It has gone all the way down to 21. It may have gone a little bit lower even. So the bigger the delta T is, the bigger this would be. In other hours, we've gotten right on 1.4, which is exactly what we predicted. So calorimetry works. This silly, very cheap equipment is great. And this is what we'll be doing on Monday in our experiment. We're going to be running some reactions and measuring what the delta H is. James?
I have a kind of random question. Did you do an endothermic reaction in an absolute zero situation?
It would not react because it needs to take in energy, and so yeah, there would be no reaction. Yep, yep. That's one of the reasons why. No, I'm not going to say that.
Wait, quick question.
Yeah.
Do you do any reaction in an absolute zero?
I don't know of any. Because reactions need enough energy to at least get started. For the reactants to break apart, you have to add what we call the activation energy. And at absolute zero, there is no energy in the surroundings. So, I'm kidding. We're good. Oh, I never gave your reading quizzes back. I'm sorry.
No, that's fine. You can keep them.
All right, I'll tell you how I graded this. There were 5 possible answers.